Okay, let's continue our discussion on the mutual inductance. We have two coils, the primary side and the secondary side. First, if we do not consider the magnetic coupling, we have the relationship between voltage and current for the primary and the secondary winding. For the primary winding, we know that the voltage V1 equals the L1, the inductance, times the di1 dt. And for the voltage on the secondary winding, that is the L2 times the di2 dt. So this is the case that we do not consider the magnetic coupling. However, if we consider the magnetic coupling between the primary and the secondary side, the current I1 will generate a voltage on the secondary winding, and the secondary winding current I2 will generate a voltage on the primary winding, and so that we use M to denote the mutual inductance. So here is di2 dt, and here is M times di1 dt, so that the V1 is a function of not only I1 but also I2, and here the V2 is not only a function of I2 but also a function of I1. And next we will discuss the polarity of M. So sometimes we have plus this voltage, and sometimes we have minus this voltage. So let's talk about the dot convention. So using the dot convention, you know when you should use the plus or when you should use the minus. So let's go to the dot convention. Okay, let's take a look at the dot convention. The dot convention states that when the current enters the dotted terminal, it produces a voltage in the coupled coil, which is positive at the dotted terminal. So we will use two examples. So you can see the dot, we have the dot on the primary winding and the secondary winding. These two circuits, the only difference is that the position of the dot on the secondary winding. So you can see that the dot, in the first example, that the current I2 enters this dot. But for the second example, the current I2 is leaving the dot. That's the only difference. So we can say that for the current I1, it enters the dot, so it produces a voltage which is positive, produces a voltage in the coupled coil which is positive at the dotted terminal, so that this I1 will produce a positive voltage. So here is a positive voltage at the dotted terminal, and its voltage is M times di1 dt. And for the secondary winding, there's current I2 which is also entering the dot, so that it will produce a voltage on the primary winding, and the polarity, which is because this I2 is entering this dot, so it will produce a voltage which is positive at the primary winding, so that it will generate a voltage which is M times di1 dt. And also we know that I1 will generate a voltage which is L1 times di1 dt. This is the voltage generated by I1 plus the voltage generated by I2. This should be I2. So this is the voltage on the primary side, V1. And for the secondary side, the same thing. We have the voltage generated by I2 plus the voltage generated by I1. That's the voltage relationship for the first example. For the second example, it's a little bit different. So this current is entering the dot. So it will produce a voltage which is positive at this dot, so that the voltage it produces is I1, IT. And this I2 is entering the undotted terminal, so it will produce a voltage which is positive at the undotted terminal in the primary winding, so that it will produce a voltage I2 dt. Right. How about the voltage produced by I1? So this is L di1 dt. And the voltage produced by I2 is L2 di2 dt. Right. So how about the total voltage V1? This L times di1 dt, this is positive at the top, negative at the bottom, but the polarity of the induced voltage by I2, the polarity is opposite, so that we have V1 equals L di1 dt minus M times di2 dt. The same thing for the secondary winding, so that we have V2, so that V2 equals L2 di2 dt, and this is minus M di1 dt, so that we have here, this is minus the induced voltage minus the induced voltage. So the only difference is the dot, the position of the dot. For the first example, the current is entering the dot in the secondary winding. For the second example, the current is entering the undotted terminal. So once it enters the undotted terminal, it will produce a voltage at the undotted terminal in the primary winding, so that this is negative, this is positive. And for the primary winding, it enters the dotted terminal, so it will produce a voltage in the secondary winding which is positive at the dotted terminal, so that which is positive at the dotted terminal. So this is plus, this is minus, right? But the reference direction I2 is selected like this, so that the L2 times di2 dt, which is the positive, negative, right? So this is the dot convention, and we will use some examples to practice the dot convention. Textbook. So we have the primary winding and we have the secondary winding, and we have the reference direction for I1 and I2. And be careful that this only the arrow or the positive or negative denotes the reference direction. It is not the actual direction. We deal with the AC circuit, so it is alternating. So this is the reference direction. So let's take a look at the primary winding. So that the current I1 is entering the undotted terminal, so that it will generate a voltage which is positive at the undotted terminal on the secondary winding, so that this I1 will generate a voltage on the secondary winding, that is M times di1 dt, so that this is positive, negative, because it will generate a voltage that is positive at the undotted terminal, because I1 is entering the undotted terminal. And also the same thing, I2 is also entering the undotted terminal, so it will generate a positive voltage at the primary winding, and it is positive at the undotted terminal, so that it will generate a voltage, the M di2 dt. This is the mutual inductance. And how about consider the self-inductance? So the current is entering, so it will generate the voltage, which is L1 di dt, right? And also this current I2 will generate a voltage that is L2 di2 dt. So for the secondary winding, the total voltage, we have the V2, and the reference direction for V2 is positive on the top, negative at the bottom, V2. So that this V2 equals the M times di1 dt plus L2 di2 dt. This equals the V2. How about the voltage V1? But be careful that the reference direction for the V1, which is the negative at the top, positive at the bottom, this is V1t. But here, our voltage is positive at the top, negative at the bottom. So we plus the L1 di dt, L1 di dt plus M di2 dt, and we take the negative sign. So this equals the V1t equals the negative of the sum of these two. This is because the reference direction selection of V1. If we reverse the reference direction of V1, for example, we put the negative here, positive here, so that negative, positive, so that we remove this one, right? So V1 equals the L1 di dt plus M times di2 dt. So this is one example of the dot convention. So the second example, we need to write the loop equation for this circuit. So do you remember the loop analysis? I think we discussed in chapter 3, right? But here we have the inductors, and also we have the mutual inductance, which is M. But it is very similar. First, we need to figure out the current flowing through L1 and L2. It is obvious that the current flowing through L1 is I1, right? How about the current flowing through L2? So the current flowing through L2 is I1 minus I2, right? So that this current I1 flowing through L1 will generate a voltage on L2. And also this current I1 minus I2 flowing through L2 will generate a voltage on L1. So let's write the generated voltage. So this I1 is entering the dotted terminal, so it will generate a positive voltage here, so that it will generate a voltage which is positive at the dotted terminal, and it is the magnitude is M times the dI1 dt. And this current I1 minus I2 is entering the undotted terminal, so that it will generate a voltage which is positive at the undotted terminal, and its magnitude is M times dI1 minus I2 dt, right? Then we can write the equation for each loop. Let's take a look at loop 1. So we have this current I1, right? So I1 times R1 plus, and this is L1 dI1 dt, self-inductance. And we have a voltage, the induced voltage here, which is negative on the left, positive on the right. So we minus the M times dI1 minus I2 dt. And here, right, we have the L2 plus the L2, and its current is dI1 minus I2 dt. And we have the induced voltage, so that is the minus the M dI1 dt, and minus V1 equals 0. This is for loop 1. For loop 2, we have this. This is R2. This is R2. So we have I2 times the R2 plus L N dI1 dt. And also we have the self-inductance, but the current, the direction of the current is opposite to the selected reference direction. So this is minus L2 dI1 minus dI2 equals 0. So that's the loop equation for the two loops. So for the self-assessment 10.1, take a look by yourself, and we will discuss on Wednesday. And also the example 10.3, take a look by yourself. And now we will discuss the example 10.4. So in this one, you need to calculate the output voltage VO. So we have two loops, the loop 1 and the loop 2. And the current I1 is entering the dotted terminal, and the loop 2, the I2 is entering the undotted terminal. So first we write the induced voltage first. So for this I1 entering the dotted terminal, so it will generate a voltage at the secondary winding, which is also positive at the dotted terminal, so that it will generate a voltage. And also the mutual inductance is given is J2, so that the voltage it generates is J2 times I1. And for the secondary winding, this I2 is entering the undotted terminal, so it will generate a positive voltage. And also the mutual inductance is J2 times I2. So that once we obtain the induced voltage, we can write the loop voltage equation. So for example, for loop 1, this is 2 ohm times I1. And the current is also entering this inductor, the self-inductance is J4, so that plus J4 times the I1. Be careful that this I1 is the phasor. And also we have the induced voltage, which is the negative positive. So we have minus the J2 times the I2 and equals 24. This is the phasor, or the current are phasors. This is the equation for loop 1. For loop 2, we have this loop, so that we have first negative J2 times the I2 plus 2 times I2 and plus this is J6 times the I2 and minus this induced voltage J2 times the I1 equals 0. And once we obtain the I1 and I2, we can easily calculate VO. VO equals the I2 times 2. So we simplify the equation and make it in the matrix form. So this is I1, I1. So this is I1, 2 plus J4 minus J2 equals 24, 30 degree. And this is I1, negative J2 times I1 plus the negative J2, this is 2, this is positive J6, so 2 equals 0. So we can write in the matrix form. So use MATLAB, solve for I1 and I2. And once you get I2, the VO equals 2 times I2. So that's this question. Example 10.5 is the last example today. So we need to write the loop equation for the 3 loops. So let's take a look. We can see that there are 2 inductors, L1 and L2. The mutual inductance is N. So let's first determine the current flowing through each inductor. For the first inductor, the loop current is I1. This loop current is I2. So the current flowing through L1 is I1 minus I2, right? And for the second inductor, this is I2, this is I3, so that the current flowing through L2 is I2 minus I3. So this current I1 minus I2 will generate a voltage on L2, and this current I2 minus I3 will generate a voltage on L1. So let's determine the voltage it generates. So we can see that I1 minus I2 enters the dotted terminal, so it will generate a positive voltage at the dotted terminal on L2, so that we can calculate the voltage generated by I1 and I2 because the mutual inductance is N. So we use J omega M times I1 minus I2 because the current flowing through L1 is I1 minus I2, so it generates a voltage J omega M times I1 minus I2. Similarly, we can calculate the voltage generated by I2 minus I3 on L1, so that this is j omega m times I2 minus I3. Because I2 minus I3 enters the dotted terminal, so that this voltage is positive at the dotted terminal. So that once we figure out the induced voltage, we can write the apply KVL on each loop. So first one is, this is current I1. So voltage drop on R1 is I1 times R. So that's this term, I1 times R. And this current is I1 minus I2. It will have a voltage drop on the inductor. So that is the j omega L1 times I1 minus I2. That's the second term. And we don't forget the induced voltage. And also it is a voltage drop. So plus j omega m times I2 minus I3. That's the third term. And also we have a capacitor here. And we have, so that we have 1 over j omega C1 times, because this current is I1 minus I2. So 1 over j omega C times I1 minus I2. And this loop, the voltage source, equals V. So that's the equation for the first loop. For the second loop, it's more complicated because there are more components. So let's start from the resistor. So that the current is I2. So this current is I2, and we have the resistor R2. So this voltage is I2 times R2. That is this term. And then in this loop, we have this inductor here, and the current is I2 minus I3. So that the voltage drop is j omega L2 times I2 minus I3. And also, don't forget the induced voltage, j omega m times I1 minus I2. And also it is a voltage drop. So plus j omega m I1 minus I2. And then it meets the resistor R3. And R3 is, this current should be I2 minus I3, R3, so that it should be should be I2 minus I3, so I2 minus I3. That's a voltage drop on this resistor. And then it meets this capacitor. And the current here is I2 minus I1. So we have j omega C1 over 1 times I2 minus I1. And then it meets the inductor 1. So that we have j omega L times this I2 minus I1. And also remember this induced voltage, because we have the reference direction from down to up, so that we have, this is a voltage increase. So we minus j omega m times I2 minus I3. So that's this term. So we have the equation for the second loop. For the third loop, so we can start from the capacitor. So this is current I3. So that we have 1 over j omega C2 times I3 plus the voltage drop on the resistor 4, R4 times I3. That's the second term. And the current here is I3 minus I2. So the voltage drop on R3 equals R3 times I3 minus I2. And also we have this inductor j omega L2 times the I3 minus I2. But we forgot here, we forgot the induced voltage. So we need to minus j omega m I1 minus I2 equals 0. So that's the equation for loop 3. And when you go back home, you need to finish the self-assessment exercise 10.2, 10.3, and 10.4, and we will discuss on Wednesday. Yeah. Thanks. See you Wednesday.